Hello everyone. Let's continue solving the problems of the chapter 2, problem 25. The transformer of problem 24 is to be used as an auto transformer. A, show the connection that will result in maximum kVA rating. B, determine the voltage ratings of the high voltage and low voltage sides. C, determine the kVA rating of the auto transformer. Calculate for both high voltage and low voltage sides. So, what is an auto transformer? Let's review the auto transformer section from the reference chapter 2, this section 2.5, auto transformer. This is a special connection of the transformer from which a variable AC voltage can be obtained at the secondary. A common winding as shown in figure 16. This figure is mounted on a core and the secondary is taken from a tap on the winding, the point B. Suppose this single phase transformer, we have this winding and this voltage V1, I1, and this secondary winding V2, I2. The number of turns is N1, N2 here. In a single phase transformer, the number of turns are constant values. And the value of the V2 is equal to N2 divided by N1 times V1. The value of the V2 is determined by V1 and this turns ratio. If we are going to have a variable output voltage, we should be able to change one of these variables, for example, N1, N2, or V1. So suppose V1 is constant. So in this case, if we have a construction, right, to be able to change N2 or N1, we can have a variable output voltage. This is the case that we have for an auto transformer. Here we have one coil, yes, and this is the input voltage V in. This is a fixed number. This is the input current, and we get the output voltage from this point up to this point. We can change the value of the V out by changing the position of the tap where we get the voltage. So in this case, as you can see, we have one coil, okay? And we have electrical connection between the input voltage and output voltage. So in a single phase transformer, these two coils are coupled only magnetically. Yes, we have this mutual flux phi m. In this case, we have this flux in this coil phi, but also we have this electrical connection between the input and the output. This electrical connection is a disadvantage for auto transformer, and this electrical separation between the input and output is an advantage of the transformer. In contrast to the two-winding transformer discussed earlier, the primary and secondary of an auto transformer are physically connected. Okay? However, the basic principles of operation is the same as that of the two-winding transformer. In this case, also we have these ratios for V1 and V2 and I1 and I2. We will check these equations and will derive them now here in this slide. Just one important point is this one. Auto means single or one, not automatic. Okay? Auto means a transformer with single coil. Here we have only one coil. So auto transformer, a transformer with a single coil. Anyway, how we can find a relationship between the V1 and V2 and I1 and I2. In this case, we have this total number of turns, and 1 is the number of turns between these two terminals, is the number of turns between two terminals of the input, and N2 is the number of turns between these two terminals, the output terminals. An auto transformer can be used to step down the voltage or step up the voltage. Here, in this case, we get a higher voltage than the input, and here we get a lower voltage than the input. So in general, we have this case. This is the coil. The coil can have a higher number of turns. Okay. This is the V in input voltage, and the output voltage is this one, V out. So if we change the position of the tap, if we increase the number of turns, we can increase the output voltage. In this case, V out is lower than V in. In this case, V out is equal to V in. And in this case, V out is higher than the input voltage. Okay, so by changing the position of the common point, the point B. So how we can derive these equations, the ratio of the voltage and currents? Consider this structure. Suppose we have this core, just like a single phase transformer, this core, and suppose we have this coil with a number of turns, right? We have just a single coil. Here we have input terminals, V1, and I want to get a connection from here, from a common point. Let's select this one, this connection, to get the V2. So this is I1 and this is I2. Suppose we have a load here. This is the load impedance. And suppose we have a voltage source here. Okay. So in this structure, how much is the value of the induced voltage for this part of the coil and for this part? Here, let's call this point A, the same as what we have in this figure. This is the point B, and this is the point C. The point B is common point where we get the voltage for the load. When the current flows in this part of the coil, this one, I1, we will have this field inside the core in this direction. Okay, so as you can see, the flux, the core flux passing through this part of the coil is the same as this one. Okay, and let's call the number of turns between A to B and S, number of series turn, and the turns from point B to C and C, number of common turns, right? So here, this is the case that we have the V1, excuse me, we have this number of series turn, and this is the number of common turns. This is V out. This is common between the V1 and V2, but this is in series with V1 only. Okay, this case that we have. So how much is the flux linked to this part of the coil? The EMF between A to B points is equal to NS, right? The number of series turns times d by dt. Okay. And what is the value of EBC is equal to number of common turns d by dt. So what is the value of the V1? V1 is equal to EAB plus EBC, and V2 is EBC. What is the ratio of V1 divided by V2? We have NS plus N common d phi dt divided by N common d phi dt. So these two are the same, okay? And we have this ratio NS plus N common divided by N common. So this summation is equal to N total, the total number of turns, right, for the coil that we have between the point A to point C. That is equal to actually N1 divided by N2. According to this figure, N1 is the total number of turns between these two terminals. N2 is the total number of turns between these two terminals. So we have this voltage ratio equation similar to what we have for a single phase transformer. But what about currents? So here, as you can see, we have the same equations for the step down and step up auto transformers, right? You can investigate these two equations. In a step down case, V in divided by V out is N total. divided by n common, and in the step up, V in divided by V out is n common. Yes, because the number of turns between these two terminals is n common divided by n total. But what about the ratio of the currents? As you know, for a single phase transformer, yes, okay, for a single phase transformer, when we assign dot points similar to what we had, right, in simpler, for example, this one, two winding transformer, you can see these dot points. What a dot point means for a single phase transformer, for a coil that we have for a transformer. Consider this core that we have these two coils, primary and secondary. So the dot point, if I consider dot point here for this coil as reference and this as the I1, the current of the coil 1, enters to the element, similar to this one or this element. Current enters to the element. In this case, what is the right direction of the field generated by this coil? Is in this direction, right? So this is the phi 1. And we have this equation, integral of h dot dl is equal to summation of the n I, right, for all coils, summation of magnetomotive forces. If I consider also a dot point here and also consider this direction for I2, the direction of the field generated by I2 is in this direction, phi 2. This is in the same right direction of the phi 1. Okay, so in this case, we can write integral of h dot dl if we consider a core with ideal permeability. This is equal to 0. As you know, ideal case, we can write n1 I1 plus n2 I2 equal to 0. So yes, this summation is 0. And in the case of a single phase transformer, if we consider these directions, the phase of the current 1, right, is in opposite of the current 2. I mean, here we have n1 I1 equal to n2 I2, negative sign. So the phase of the I2 is 180 degrees out of the phase I1. If we consider this right direction for the currents and this dot point. So let's check it in the software. For problem 25, let's generate a new simpler model and check this point at a single phase transformer. Yes, number of turns ratio 1, add a voltage source and a resistor. So let's set the value of the voltage equal to 100 RMS value and the value of the resistance equal to 100. Okay. Do the connections to check the value of the current for the primary coil and secondary coil of this two winding, right, transformer, a single phase transformer that we have. So let's add an AC solver. The start frequency 50, the end frequency 60 hertz. Okay, just solve the circuit for these two frequencies. Let's analyze to check the numbers. From here, data table, we are going to add the I1, the current of the primary coil. Okay, also I2 and R1 dot current. I will add it. So display it in magnitude and angle. As you can see, the phase angle here for I1 is 0, for I2 is 180. I2 is 180 out of the phase of the I1. Yes, this is the reason. Okay, because this is the convention, this is the direction of the current. But what is the current of the R, the load is in this direction. Okay, so here if I also add the current of the resistance 1, yes, magnitude and amplitude, this is in the same phase with I1. Yes, because the resistor current is negative of I2. So if I consider this direction as the reference direction for the coil 2, we can write this N1 I1 equal to N2 I2. So we will use this equation. In this case, the current I1 enters to the primary coil, but the current I2 exits from the secondary coil. So we can write this equation considering these directions. Yes, if you add right another coil here, if you add another coil here, you can use the same dot point, right, as reference of the current. If you consider currents, right, all currents enters to dot points, you can write this summation and j I j, right, j equal to 1 to the number of coils that you have. So anyway, this is not our case. Our case is just right, 2 coils. So what is the case for an auto transformer? Here, consider this step down case. For example, this is the I1 and this is I out. The current in this branch, if we consider this reference direction, this is I out minus I in. We can write this magnetomotive force balance equation. In this case, I in enters from the dot point and this current exits from the dot point. So NS times I in is equal to N common times I out minus I in. We have this balance for the magnetomotive force if you consider integral of H dot dl equal to 0. So here, if we consider this reference direction, this is the field generated by this part of the coil. And here, in this case, if we consider this reference direction, okay, this is the field generated by this part of the coil in opposite directions. So if you are going to have magnetomotive force balance, we should have this right equation. So yes, I in divided by I out minus I in is this one. And if you add the numerator to the denominator, we will have this equation I in divided by I out is equal to n common divided by n total, right? Similar to a single phase transformer. We have a similar equation for the step up auto transformer. This explanation is here. This is the magnetomotive force generated by the upper half, right? Lower half, we have this balance, and finally, we can write this equation. The voltage and currents are related by the same turns ratio as in a two-winding transformer. So, this is the case, right, that we have for a step down and a step up auto transformers. You can justify this equation. Again, we have V in, I in is equal to V out, I out, power balance. If we neglect, right, losses for the core, right, and the windings, the resistances that we have for these coils, we write this balance equation. So now let's consider this point. We have this important concept. Because we have electrical connection, right, between the input and output of an auto transformer, we will have conductive power transfer. Yes, we directly connected the output to the input, but also we have inductive power transfer, similar to a transformer. How much is the ratio? How much is the total power is conductive and how much of it is inductive? In this case, for this step of auto transformer, let me display the case. Here we have this coil, and this is the V in, this is the load, okay, ZL, and here is N common, this is NS. We have this equation S, the volt ampere, the apparent power, is equal to V out I out. What is the value of the V out? You can write a KVL here. V out is Vs plus V in. Okay, this term that is equal to V in I out plus Vs I out. These two products. So we have this. This is the V out for the load. S is V in I out plus Vs, this voltage, Vs times I out. What is the case here? The equivalent circuit, we have a load here, ZL, and we have NS here. We have one source here, okay? If you consider ZL and you need to calculate the current of the ZL, we have one common number of turns here, right? Okay, so this is the number of common turns. Anyway, this is the value of the current. I out, how much is the power that is delivered by this source to the ZL is V1 or V in times I out. This is the amount of the power delivered by this source, this one. Okay, so this is conductive portion of the apparent power. And also we have this coil here, we have a EMF in it. We can consider it like a voltage source. How much is the power delivered to the ZL by this inductor is Vs I out. So this is inductive part, inductive, and this is conductive. Okay, so we can find the ratio of the inductive power transfer to the conductive one. Simply, yes, if we multiply this by V out divided by V out, we will have this S is equal to S, right, times V in divided by V out plus S times Vs divided by V out. This is the inductive, right, portion, this one. Inductive, and this is conductive. You can write, do the same for a step down autotransformer. So finally, what is the ratio of the autotransformer apparent power to the inductive one is equal to this, right, fraction n total divided by n s. N total divided by n s. The ratio of the autotransformer apparent power to the inductive, right, part. So yes, if we have a single phase transformer and use two coils and construct an autotransformer, we will have a right higher value for the apparent power, and we can find the relation using this fraction. So this is the question, the problem that we have. Show the connection that will result in maximum kVA rating. We have these four cases. Yes, in the case 1, we have the high voltage winding here, low voltage winding here. The input voltage is voltage of the high voltage plus VLV, and we pick up the output voltage from the low voltage winding. Okay, this is the case 2, case 3, and case 4. Case 1 and case 4 are the same. Yes, just the direction of the power flow, right, is reversed. For the case 1 is in this direction, for the case 4 is in opposite direction, right? These are the same. Case 2 and 3 also are the same. We have these ratios. And considering these ratios, we have this number in fraction, ns, number of series turns. The numerator is the same for, right, these two cases. So when we have a lower number of series turns, we have, right, a higher power if we do this type of the connection, the case 2 or 3. What is the value of the autotransformer power in this case? Is this one. This is the, right, rating of the transformer in problem 24, 10 kVA, and these are voltage ratios. So Here we have, this is the transformer apparent power times 2400 plus 240 divided by 240. The apparent power of the auto transformer is 110 kVA. 100 kVA, right? Conductive, 10 kVA, inductive, the same as the transformer. So this is the apparent power of the auto transformer. Part B, determine the voltage ratings of the high voltage and low voltage sides. So in the case 2 and 3, the voltage, of the high voltage side is this summation, and the low voltage side is equal to the voltage of the high voltage winding, the part 2 or the part 3. The voltage of the high side is this summation, and the low side is 2400. Determine the kVA rating of the auto transformer. Yes, we calculated it here. Calculate for both high voltage and low voltage sides. Let's use these two equations, V in I in and V out I out. How we can use these equations? This is the value of the current for the high voltage winding, 4.16, and this is the value of the current for the low voltage winding, 41.6. For the case 2, V in times I in is this voltage times this current, V out times I out, right? For both cases, we have 110, 110, 110 here. For the case 3, you can see the value of the currents and voltages. So why the value of the current is IHV here and ILV here? Yes, this is the rated current that this coil can tolerate. This is the rated current that this coil can tolerate. And in maximum case, we will have these currents in these two coils, and we'll have this maximum current, for the rated condition. We should calculate the rated power of the auto transformer. Let's investigate this using an example in the Simplorer. Suppose we have this single phase transformer, this coil N1 and N2 here. This is V1, V2, I1, this is I2. Let's consider the rated voltage here 100 and the rated voltage here 50 volts, 100 volts. And I'm going to consider the rated apparent power of this transformer equal to 1 kVA. Okay, so what is the value of the rated current for the primary coil? Is 10 amps. For the secondary is 20 amps, 20 times 50 is 1 kVA. So if I consider a resistive load here, R, and a source here, I can simulate the transformer for a rated operating condition. What is the value of the power for the load? Is V2 to the power 2 divided by R. Here I considered the turns ratio, 2 by 1. So V2 is 50 to the power 2 divided by R is equal to 1000. I can calculate the value of the R. How much is that? Is 50 to the power 2 divided by 1000. 2.5 oh is the value of the R. So when we set the value of the R equal to 2.5 and apply 100 volts here, we have this rated power. So let's generate the model. Delete. No, just let's add wattmeter to measure the value of the output power. This is the problem 25. Okay, the value of the voltage is 100. Turns ratio, as you know, in the simple order, turns ratio N is N2 divided by N1. That is equal to 0.5 in our case. So this is 0.5. And I am going to set the value of the resistance equal to 2.5. Yes, let's pick up wattmeter from the measurement. Here, electrical, this. So here is the current. Also, we have dot point for this measurement tool. And I should connect, right, the voltage here. We pick up the voltage and measure the power. So analyze to check the value of the power. So from here, data table, let's plot the magnitude of the current of the primary coil. Magnitude from here. Magnitude phase is not important. Magnitude and the real part of the power. These three numbers. Yes. The value of the current for the primary coil is 10. 10 for the secondary 20. And the value of the power is 1 kilowatt. So now I want to use this transformer, reconnect, right, terminals to build up an auto transformer. We have these two coils, okay, for the transformer, this high voltage winding and this low voltage winding. Dot points are important. The direction of the current. Let's consider the case 1, for example. In the case 1, here is the common point. Yes, also if you consider these dot points, this is the common point. We should connect this terminal to this terminal. Connect this to the input voltage Vin and this one. For Vin, also we get the load from here and here. This is the load resistance. So this is the case 1 that we have here. In this case, how much is the value of the power of the auto transformer? We can calculate it using this equation. Let's justify that, this equation. NHV, this is S of the auto transformer divided by S of transformer. This is 1 kilowatt is equal N total. That is NHV plus NLV divided by NHV, number of series turns, NS. This is 1 plus NLV divided by NHV. That is equal to 1.5. So the rated power of the auto transformer that we calculated is 1.5 kilowatt. This means that if we have 10 amps in the primary coil and 20 amps for the secondary coil, we can get this power. We know that primary coil can tolerate 10 amps. The secondary coil can tolerate 20 amps. Yes. So here, let's perform these connections. I need to delete, right? This here. We have this connection. This is the input that we have. Okay. And we get the output from here. This is the current voltage and this connection. Consider that we did these connections properly. If you do connections wrong, the field, right, generated by this coil can be in the same direction of the field generated by this coil. So we have a subtractive case. We can have additive EMFs or subtractive. Subtractive is useless, right? So we focus on additive case. And here you can see the cases that we have these dot points. If we place the dot point here and wound the coils in opposite directions, so okay, you can investigate that, not important. So what is the value of the power in this case? We should set the value of the voltage, in this case, equal to 150, because these two coils, right, the rated voltage of the primary is 100, secondary is 50. So in total, when we connect them like this, the input voltage, right, can be 150. This case 1, the summation can tolerate this rated voltage. Let's consider R2 equal to 2.5 and run the simulation. Then we can compare. So in this case, let's add the I1 of the right TWT2, the magnitude and power of the second resistor. As you can see, for both cases, we have the same output power. But for auto transformer, the current of the coil, the high voltage coil, is 6.67, right? Lower than the rated one. So this means that this coil can tolerate a higher value for the current without thermal overheating, because the rated value is 10. And also we can increase the value of the current for the right low voltage coil. So if I reduce the value of the resistance to increase the value of the power, we can check that. In this case, how we can get 1.5 kilowatt power if we set the value of the resistance equal to 1.66, this one, and let's rerun the analysis so we can check the numbers. Here in this case, as you can see, we have rated currents for I1 and I2 similar to the transformer, but we are getting more power, right? 0.5 kilowatt conductive. Okay, so yes, we can do this kind of simulations in this powerful software. Now you can realize what we mean if we, right, reconnect a single phase transformer to make an auto transformer. So you can consider case 2, 3, 4 other cases and try to do simulations, check the numbers. We did it for the case 1. Anyway, so you can repeat the calculations. Investigate problem 25. Let's go for the next problem. Problem 26. A single phase 10 kVA 460 to 120 60 Hz transformer has the efficiency of 96% when it delivers 9 kilowatt at zero point 0.9 power factor. This transformer is connected as an auto transformer to supply load to a 460 volts circuit from a 580 volts source. A. Show the auto transformer connection. B. Determine the maximum kVA of the auto transformer can supply to this circuit. Determine the efficiency of the auto transformer for full load at 0.9 power factor. So here we have 4 cases. Which one is compatible to this problem? As you can see, the load is equal to the load voltage is equal to 460. This is the load voltage. Input voltage is 580. So we have this situation for the case 2. Okay, this is the value of the high voltage winding, this one, and this is 120 volt for the low voltage winding. So this case and this case is not possible. This case, the number 3 also is not possible, and we have the case 2. In this case, determine the maximum kVA rating. Yes, the rating of the transformer STR is 10. What is the value of the auto transformer apparent power? Total divided by number of series turns, NLV. This fraction is equal to the voltage fraction, right? We have the direct relationship between the number of turns and voltage. So this is 580. This voltage divided by the voltage of the series part, 120. The rated power of the auto transformer is 48.33 kVA. This value. Let's check the number from the reference transformers for this problem 26, part B. And how we can calculate the efficiency for the auto transformer? Here is the definition of the efficiency. The rated power of the transformer is 10 kVA. It delivers full power. Okay, the active power is 9 kilowatt. The power factor is 0.9. So it delivers the rated one. And we have the efficiency for the rated condition. Okay. So here 0.96 is equal to 9 kilowatts. 9 kilowatts plus the core loss plus the copper loss. So summation of core and copper loss is equal to 375 watts. We have this amount of loss for core and resistance of the primary and secondary coils. So for the auto transformer, for the condition here, 0.9 power factor, what is the value of the efficiency? This is the apparent power. We calculated it here. Times 0.9 is the active power. load fraction is 1, rated 1. So we have this amount for core and copper loss the same. The efficiency will be equal to 99.2. The efficiency of the auto transformer is higher than the transformer. What is the reason? Because we have the same amount of core and copper loss, but we are delivering more power. Yes, this is the reason. Here you can see the same number, yes, for this problem. So you can repeat the calculations for solving auto transformer problems, right? You need to consider these conditions. Also, we have these important equations. Anyway, okay, so let's solve the next problem, problem 27. Reconnect the windings of a single phase 3 kVA 240 to 120 volts 60 hertz transformer so that it can supply a load at 330 volts from 110 supply. So among these four connections, the connection number 4 is possible, right? Because the load voltage is 330, the voltage is higher than the rated voltage of the coil 1 and coil 2. So 240 plus 120 is 360. This is lower than the rated value of the voltage that we can have. So the connection number 4 is okay because the supply is also 110, is lower than this rated value. We can connect this supply to this coil. If this is higher than 120, this is not possible because this is higher than the rated value here, the value of the voltage that this coil can tolerate. So the connection 4 is possible. Determine the maximum kVA of the reconnected transformer, right? Here we have this equation. S auto transformer divided by the S transformer is N total divided by NS. This equation is the same, right, for a step up and a step down transformers. So this is N high voltage plus N low voltage, the total. The series term is high voltage, okay? If you replace the numbers, these rated values that we have here is equal to 4.5 kVA. Just consider that you shouldn't use these two numbers, right? This is the load and this is the supply. We are going to find the maximum kVA. We can increase this up to 360 and increase this up to 120. So to calculate the maximum rating, we use the rated numbers. 4.5 kVA is the maximum apparent power that the auto transformer can deliver. Okay, so this is enough for this video. You can practice problems of the auto transformer section, and let's continue in the next video. Thanks for watching.